Welcome to SLO6, video 3. We'll be discussing making and using Grignard reagents in the so-called Grignard reaction. So we'll get started by thinking about how we would make a Grignard reagent. These are compounds that contain a carbon-magnesium bond. And we've already actually seen this back in video 1 where we discussed the action of magnesium metal itself, so like Mg0, and an alkyl halide. And these make compounds that we call Grignard reagents colloquially, but they also have specific names. That's basically whatever the alkyl group is, magnesium halide. Right, so you could say something like methyl magnesium bromide or ethyl magnesium chloride. You get the idea. So let's look at a few examples just so you can see what this looks like in action. We would take some kind of an alkyl halide, like for instance our example back from Grignard's original experiment, iodomethane, and use some metallic magnesium. And this magnesium would affect the oxidative insertion, wherein it pries the iodine and the carbon apart and puts itself right in the middle. So the most descriptive way of writing the structure of the product would be something like this, where we actually show the magnesium carbon bond as well as the magnesium halogen bond. The magnesium halogen bond is almost assuredly ionic. It turns out that these bonds are semi-covalent, which is a little surprising. We typically think of metals as only forming ionic interactions, but this bond here is like highly polarized, but covalent. Cool. So it's a little tedious to draw the structure all the time, especially for reagents that get used quite a bit. So there's a couple of other notations that chemists use to describe this kind of a structure. So we could say something like, just writing out a formula. Right, so just an H3CMg, so there's an implied carbon-magnesium bond in there. If we felt like even lazier, and because, well, I'm an organic chemist, I am lazy, I'm just going to write methyl, or Me, Mg, I. So this would be Me. Yeah, these don't work very well. It sounds like I'm speaking like some Vulcan language or something. So 3 different ways of representing the structure of the product. What's key is that you know which atom within these reagents is in fact nucleophilic, right? So our carbon that's actually bonded to the metal, that's our nucleophilic site, right? In this case, the carbon that's bonded to the metal will be our nucleophilic site. The downside of the most effective, or rather the most efficient way of writing these structures is that you lose track of the carbon. So methyl, the implication here is that there's a carbon-magnesium bond and that the carbon of the methyl group is nucleophilic. Right, so C of Me is nucleophilic. Right? So I'd encourage you to be able to use any of these types of notation. You'll find that in the SLO problems, I typically will use the notation that most organic chemists do. All right, so we can look at a couple of other examples here just so you have a full fleet of kind of permutations that you could think about. We're not restricted to simple alkyl groups, so benzene rings are also appropriate. So let's look at a reaction involving an Ariel Chloride, and the same kind of idea would apply, where we would react this with metallic magnesium, and we would again affect an oxidative insertion where the magnesium ends up bonded to the carbon, as well as the halogen, and specifically where that halogen was bonded to the carbon. Okay, so this structure here we would write as either the whole structure. We can also abbreviate a benzene ring, which is a substituent, I guess, on the magnesium, as a phenyl group. So we could write phenyl magnesium chloride. And again, if we were very lazy, we could write pH, which is an abbreviation for phenyl, MgCl. So again, it's important to know which carbon within this abbreviated group is the actual nucleophilic atom. In this case, it'd be one of the carbons of the ring. Okay. So we could also do this kind of a oxidative insertion process for alkenes. I'll choose an alkenyl bromide here. All right. And so you can probably predict what would happen. The magnesium will go where the bromine is. So specifically, that carbon-bromine bond is disrupted and the magnesium goes between it. Right? That doesn't mean the magnesium bonds to any carbon you want. It's specifically where the halogen was. Okay, so that would be our kind of a product. So these kinds of groups don't necessarily have good abbreviations, right? So you would typically draw the structure out. I guess you could name it. Naming is really only something that I care much about for the simple alkyl substituents, like methyl magnesium iodide in this case, or phenyl, just because we're going to use those reagents a lot. I'll probably end up describing them verbally, and it's helpful to know. If we're using a more complex looking Grignard reagent, then I'll just be drawing the structure and pointing at it a lot. Okay, so then the last example that I wanted to choose is the halogen that's missing. So I've covered my iodine, my chlorine, my bromine. What about fluorine? So we could think about some kind of an alkyl fluoride, react this with magnesium. And if you've been paying attention over the course of Organic 1 and Organic 2, you might have been starting to notice that a lot of times when we talk about things as like all halogens do this, it's really chlorine, bromine, and iodine that we're describing. Fluorine has its own set of rules. It's a very strange element, isolated up there in the far northeast of the periodic table. It's like a Mainer, maybe a little bit out in the woods, kind of grumpy, doesn't really want to hang out with anyone else. And that turns out to be the case here also. This reaction actually doesn't work, right? So we actually don't use alkyl fluorides for this. So we can make Grignard reagents from carbon chlorine, carbon bromine, and carbon iodine bonds, right? But notably not carbon fluorine bonds. Okay, so this is essentially how you'd always be making Grignard reagents, at least in this class. If you're interested in organic synthesis, or you're maybe a chemistry major thinking about research and want to do synthesis, know that a lot of the cases we actually buy these compounds, right? So like methyl magnesium iodine, you can buy quite literally in like a tanker car, right? So huge amounts of it. Same with phenyl magnesium chloride, and most of the simple species like ethyl and propyl, whatever. These more complicated structures like this, you just not start being able to make them, okay? So in a lot of cases in the SLO problems, you'll actually notice that these reagents are given to you, right? So you're not always going to have to be making them all the time, but it's important to me that you kind of have a general idea about, well, yeah, you treat it with a metal. Okay, so we're going to switch gears now, and I'm going to go ahead and clear the board, and we'll look at how we actually use these types of reagents in what are called Grignard reactions, which is exactly what we saw in video 1, making a new carbon-carbon bond from a carbonyl. Okay, and we're back. So I've cleared the board. We're going to be looking at some examples of Grignard reactions now. So like I said at the end of the first section of this video, you would typically already have a Grignard reagent either that you've made in a flask or maybe that you bought. So we'll be focusing on what those reagents themselves do with different kinds of carbonyl-containing functional groups or different kinds of electrophiles, really. So we'll go through this in a set of examples, right? So the most common one probably is with aldehydes. So I'm going to choose some relatively simple structure since my board is not particularly long here. And we can go ahead and react this with, how about ethyl, so ET, magnesium chloride. So if I'm thinking about these two compounds together, I could actually use a little bit of mechanistic reasoning to help me by identifying an electrophilic site and a nucleophilic site. So our carbonyl carbon will be at the electrophilic site, and the carbon of the ethyl group that's actually attached to the magnesium is the nucleophile. Right? So what that would end up looking like is I would do an addition. The CO pi bond would disappear, and in its place I would effectively have an ethyl group bonded to the electrophilic carbon. So the product would end up looking like, I'm going to show the new bond in red. So I would attach my ethyl group. Not blue, it's not what I wanted. And I've got my oxygen. But what's on the oxygen now? Oh. But I should have an alcohol, but I need a proton. So where am I going to get a proton? Right, water workup. So I want to make sure that I do this in 2 different steps, just like the LAH reduction. So the first step or stage of the reaction would be to actually introduce the aldehyde and your Grignard reagent, mix them together, go do, I guess, American things. What would cocktail? Craft beer? Probably craft beer. And then after that, you come back and add some water as part of your workup. Okay, and so this water workup is what actually gets you your proton as part of your alcohol group, right? So we formed a new carbon-carbon bond, right? We've also have an alcohol here, so we've taken an aldehyde and converted it into a secondary alcohol. So we could look at another example now, where we change the nature of the carbonyl electrophile, so we could look at a ketone instead. So we'll look at cyclopentanone, and we know that we need to actually separate our addition and workup steps here. So let's use a different kind of a Grignard reagent. I'm going to actually draw the structure out now. So this one here, and then we know we're going to need a water workup at some point. Okay. So just like before, I want to identify the electrophilic site. This is going to be my carbonyl. And my nucleophilic site, now I have the whole structure of the Grignard reagent, so I'm going to find specifically that it's this carbon here that's nucleophilic. So in the product, I'm going to have to attach what I've labeled as E plus to what I've labeled as N. And I'm going to have to do that by breaking a CO pi bond, but that means that the 5-membered ring is not changing. So if I actually were to draw a product structure here, I would still have this framework. I know I would have an OH group. And now I need to think about the new carbon-carbon bond. Right? So I'm actually going to put the labels from my reagents onto the product to make sure that I can see that the electrophilic and nucleophilic sites end up being bonded together directly. So this atom here is our electrophilic site. Excuse me. We're going to make a new carbon-carbon bond. I'm going to show that individual new carbon-carbon bond in red. And then I need to think about this 3-carbon unit where this carbon that's not a part of the alkene is the nucleophilic site. All right, so there's that carbon here, and then there's the alkene. So if I look at this chain, I've got 1, 2, 3 carbons. 1, 2, 3 carbons, that looks good. And then again, just to make sure that I've done everything correctly, I want to make sure that the nucleophilic site they identified in the reactants is actually where I think it needs to go. Perfect. So I've connected those two. All right, so we could look at another example. So let's look at an ester here. We'll look at ethyl acetate. And let's use phenyl magnesium bromide. And a workup. All right, and so here, something a little bit interesting happens. If you actually run this reaction and you then isolated the product and took an IR, you would see no carbonyl, but you would see an OH peak, which suggests to me that you've actually done 2 different additions. So if we look at our carbonyl, this is our electrophilic site. We also know that that carbonyl is at the +3 oxidation level. So if I actually introduced a nucleophile, like a phenyl group, onto this electrophilic site, I'm going to reduce the carbon by 1 level. That gets me to a ketone functional group, right? Okay, and then if I have a ketone, well, I already know that I can react ketones with Grignard reagents, so I actually add 2 equivalents of the nucleophile. So I'm going to end up with two different phenyl groups incorporated into the product. So I've got my OH, IR tells me that's there. And I've got two new carbon-carbon bonds now. I'm going to show them both in red. So I've got one phenyl group, two phenyl groups. So I've got a tertiary alcohol. And I actually want to think about what else I'm forming. This whole group here, this ethoxy group, is going to serve as a leaving group. So this example is a little bit different, right? We're dealing with the carboxylic acid derivative here. We know when we actually encountered this with lithium aluminum hydride reductions that it's really not possible to do just one of these kinds of additions, because once I form that first addition product, I now have a reasonably good leaving group. That wasn't the case for aldehydes and ketones, so these function in a slightly different mechanistic way. Carboxylic acid derivatives undergo double addition. So first through a snack mechanism, and then through an addition. Okay? So it's not possible to stop at the ketone here. I'm going all the way from a +3 electrophilic site to a +1 site. And that's where this double addition kind of concept comes into play. All right, so there's one other permutation that I want to address, and that's the reaction of Grignard reagents with amides. Right, that's your nitrogen-containing functional group, or carbonyl functional group. These don't react. So amides plus Grignard reagents, no reaction happens. This is complex. There are examples in the chemical literature where this happens, but they're unusual. They don't always work. They're very finicky. So for our class, we're going to assume that that's really not viable. And in any case, the rates are usually very low. So at this point, you basically can make predictions about that column in the carbonyl reactivity chart that you were using before spring break, and that blank is still available on Brightspace, where you can now fill in the column going from acid chloride all the way down to amide. Right? In the next video, we're going to be looking at some special instances where Grignards react with nitriles and with carboxylic acids. At this point, you can do a lot of the box problems in SLO number 6, at least those involving functional groups as electrophiles that are not nitriles or carboxylic acids. So I'd encourage you to do a few of those problems before you watch video 4.